Greetings. Today is Monday, August 25. I apologize for the complexities we've been having this semester, but please bear with me and things will get better. So I'd like to continue from our last lecture. And in the last lecture, we kind of ended, we were talking about the simple hydrogen atom and how we try to generalize that to the periodic table, how when we go to the periodic table, it's not a perfect uh, match. We talked about units here, but that what you actually have is what you actually have is a situation where the different atomic species, their energy levels don't match up perfectly. And as a result, you can have situations where an energy level may be lower in energy and an electron will hop over. And this is the basis for ionic bonding. Ionic bonding, you wind up with one species, your cation, that's positive charge, one that's negative charged, and due to the Coulombic attraction, you wind up with these being bonded to one another. Really going from simple Coulomb attraction to a large scale crystal, it becomes a little bit more complicated because you're dealing with infinite sums of long range positive and negative charges. But for here, it's sufficient to discuss in this fashion. Now, when you have these attractive forces, you would think that, well, these atoms should just keep coming together until they crush each other, and they don't, because at some point you start to have repulsive forces that turn on that are very strong, and these are due to the orbital overlap of the core electrons and their associated Pauli exclusion principle, and then electrostatic repulsion because you have the overlap of these charges. And it's not uncommon to represent the repulsive energies in a power law going 1 over r to the n, and that n is picked to accurately describe what is observed in the repulsion. So this is discussing ionic bonding, and that's a it's omnidirectional, shall we say? So it's the positive and negative charges attract opposite charges and repel like charges uniformly in all directions. Uh, but going from that, we can discuss a second type of bonding called covalent bonding. And covalent bonding, oftentimes when we teach this to students, we talk about this as electron sharing. And it kind of is. A better way to think of it is it has to do with the overlap of the potentials, the nuclear potentials, allowing for electrons to interact. And what I mean by that is that if you have your nucleus, you have some potential energy that's going to go in this Coulombic shape. There is some, let's call it a degree of charge shielding as well, but you have these going out, and then this one going out. And where you have this overlap, they come together, so you get a net drop. And the covalent bond is going to form in that area. It's worth pointing out that the covalent bond has to do with the curvature and the kinetic energy of the wave function. So where you have potentials like that, you'll have a wave function that looks like, I'm just going to rough it in like this, like this, and another one that looks like this. And not drawing very well today, am I? And like this, call this psi 1, psi 2. And as a result, you can talk about the interaction. And a simple way to talk about it is through a summation where we could get psi 1 plus psi 2. And you would get something that looks like this. Or you can get psi 1 minus psi 2, or you would get something that looks like this. Now, where you have this buildup, this is the shared electrons or the bond charge. And here you have an absence of electrons, remembering that your charge density is the mod squared of the wave function. You have a node or no electrons. And since the electrons, they have to be, they have to add up to one, that means that essentially the electrons are being pushed away from the bond charge. So this we would refer to as a bonding configuration, and this anti-bonding. If you go into the mathematics, you will find, and you've seen this probably before in your chemistry class, some expression where you've got, say, two atoms, and as you push, sorry, this is energy, and as you push those atoms toward each other, they start to overlap and they start to bond, and you wind up with splitting, you have bonding, and anti-bonding. So in the case, for example, of hydrogen gas, you get two electrons occupying the bonding. You get this bonding energy that is restored, and therefore the structure is more stable. And if you try to occupy with additional electrons, they're going to go up into this anti-bonding state and decrease the capacity for bonding. And it's worth pointing out that this is a very ideal case looking at hydrogen gas. Uh, Really, you wind up with atomic states that don't exactly match. So, for example, you might have something that looks like this. And when you bring these two atoms together, they still can split. And the electrons will still occupy this lowest state, bonding and anti-bonding. But if you work out the shape of the wave functions in the orbitals, you'll find that the electrons tend to group toward the atom that has a greater electronegativity. So in this fashion, you can get a combination of uh, bonding and so covalent and anionic bonding. So it's also worth pointing out that covalent bonding, unlike ionic, is directional in nature. For example, water. In water, you've got oxygen, you've got hydrogen, and you wind up with a 104.5-degree angle that fits between them. And this has to do with bond hybridization. And without going through a lot of the details here, I want to point out that the reason of this bond hybridization happens is because the oxygen has a 1s2, 2s2, 2px, 2, 2py1, 2pz1. Valence electrons, and your hydrogen is 1s1. So the hybridization that results in directional bonding is due entirely to the electronic structure. So again, when we talk about structure being key in materials engineering, we can talk about, you know, crystals. The crystals have a particular shape, they have a particular set of directional bonds, and the directional bonds are tied to electronic structure. So you may have a macroscopic property due to the microstructure, due to the crystal structure, due to the bonding, due to the individual electronic structure. So that's covalent bonding. Let's continue and talk a little bit about, very little about metallic bonding. Metallic bonding, I think what's important to say about metallic bonding is that there are, well, almost no metallic molecules, right? There are metals, but not metallic molecules. That's because metallic bonding really is due to having a crystal, and two, is due to a quantum mechanical effect that, for here, I'm just going to call it block waves, that require the symmetry of periodicity. And yes, there are, I guess you might call them metallic clusters, right? You can get, say, sodium dimers and things like that, but that's really not the same thing as metallic bonding. So metallic bonding, you get these block waves, and as a result of these block waves, the lowest energy structure, lowest energy electronic structure, to specify electronic versus, atomic, delocalizes the electron's wave function across the crystal. And when we teach our intro to materials class, we tell students this is the so-called sea of electrons. And it kind of is, but it actually is a fairly complex quantum effect, and you should just be aware that it's not as simple as we make it sound and as the textbooks do. Kind of the irony here is that all through these introductory textbooks, we use metals as the archetypal materials. Oh, let's talk about iron and use iron to discuss the crystal structures and discuss bonding and discuss diffusion. But really, the bonding and the quantum mechanics behind iron is significantly more complicated than uh, covalent bonds or ionic bonds. And now, concluding the discussion of chapter 2, I'd like to discuss van der Waals. Van der Waals bonds, or some people call it secondary bonding. And I know people call it secondary because it's weaker. It's around uh, it's around 2 orders of magnitude weaker than your typical covalent or ionic bond. But at the same time, they're actually quite important and play a significant role in materials design. So in van der Waals bonding, you are really looking at Coulomb bonds that are localized, and you have bonding between two entities due to Coulomb bonding. And there are three classes, three classes of van der Waals forces I'd like to discuss. First is London dispersion forces. In the case of London dispersion forces, you have two induced dipoles, and those induced dipoles are attracted to each other. And a good example of this are the noble gas elements. Noble gas elements can bond to each other, and they can form a simple face-centered cubic crystal. So they can solidify, but they don't bond by covalent bonding, and they don't bond by ionic bonding. They bond by these van der Waals bonds. So you have some electron cloud and your nucleus, and another electron cloud, say two of these sitting next to each other. And the positive and the negative average, because the electrons are moving around rapidly, are centered. Now, when they come to each other, you might have just a slight perturbation in which the electrons, for example, get shifted off center just slightly, leaving your positive and negative to have a slight dipole. And if it's near enough to a neighbor, that will induce a similar shift in which they bond. So London dispersion forces are two induced dipoles. The second I'd like to discuss is called Keesom forces. In the case of Keesom forces, you have two permanent dipoles bonded. And a good example of this is water. So liquid water, you've got your oxygen and you've got your hydrogen. The hydrogen is basically a bare proton, and your oxygen is negative. As a result, you've got a dipole here that you've induced, right? You've got a dipole. And you can have another water molecule that is then bonded through hydrogen bonding, which is a form of a Keesom force. So it's the same basic principle, same relatively weak. I mean, you can pour water, right? Even though you have this bonding in the fluid. Uh, but the difference between Keesom and London dispersion is one has two permanent dipoles and one has two induced dipoles. And as you can probably imagine, the third one is the Debye forces. In this case, one induced, one permanent. And a good example of this would be, for example, a polar molecule that comes and touches the surface of a metal, right? So let's call it a right where the molecule with a permanent dipole induces charge transfer on the surface, resulting in a bond. So these are the three ways to discuss van der Waals bonding. The same principles hold. We just use a different language for the different types of bonds. So this wraps up what I like to cover from chapter 2 of Callister, and I will begin a new lecture starting with chapter 3.